Hi everybody. What I'll try to do now is to give you some general overview about the hydrodynamics affecting fine sediment transport at the Amazon shelf. So this first presentation is mostly about residual velocities in the shelf and the divergence of these residual velocities. All right. We are studying this with this model. It's Delft 3D, 10 layers in the vertical. This is the domain between Maranhão and the Orange Cape. We have the whole river inside the model, and we are really interested in that cross-section of the North Channel. That's the main entrance to the Amazon. So the model is being forced by river discharges, tides, and winds. So here we have a detail of our region of interest. I'll try to be quick in this one. Well, these are previous studies. We were very interested in the salinity front displacements and trying to make relations between the forcings and the variability of the salinity front position. And then we started to look at the residuals in the same way. So I'll show some results. Here we have bottom residual velocities for the Amazon. First, we'll compare wet period and dry period high discharges below and low discharges above. What we see is that between dry and wet season, we see some intensification in the seaward residuals, although it's not that high when compared to the difference between neap and spring tides. What happens is that when we look separately to the barotropic and to the baroclinic components, we see that the barotropic increase of residuals is quite intense, but in other way, the baroclinic changes in the opposite way. So the shoreward intensity of baroclinic residuals is much stronger during the high discharges due to higher freshwater inputs than when we are in the dry. So we have a negative feedback between these two components. So the resulting effect is not that strong. For instance, when we go to the comparison between neap and spring tides, we see that the difference in residual velocity intensity is much higher. That's because both components are changing in the same way. So the barotropic component is stronger during spring tides, and also the shoreward baroclinic component is less intense. So we have a positive feedback between these two components. Let's try. Well, actually, what we were trying to do is to understand what really governs the formation of estuary turbidity maxima and sediment deposition, and we're trying to find out how does these zones displace in time and intensity. But what we will see next, let me see. I'll pass it through. Let me see. That's quite an interesting result. Is when we look. That's what we believe. That's the main. That's going to be influencing the sediment concentration the most. When we see again, all right, which is just a scale. Red scale. Hot colors are for convergent flow, and blue scale is for divergent flow. What we see here is that in the wet period, in the frontal zone of the estuary, and this convergence occurs a little bit out seaward from the dry period. But once again, when we look to the comparison. And the points that quite different. We have in the spring tides the convergence zone occurring really outside the estuary, while this convergence zone moves about, let me see, I forgot to put, but it's about something around 100 kilometers shoreward. So again, when we look to, we can see it in the vertical structure of these velocities that are being generated. And there's some interesting things here too. Let me see. What we see is in the dry period, the maximum convergence zone occurs about 30 kilometers shoreward. This zone is governed by baroclinical effects. Here we have a zone governed by barotropic effects. It doesn't change that much. This region is where the sandbanks of the Amazon are formed. But again, when we go to the spring nip cycle, we see the major differences. The convergence zone during nips is about here, 40 kilometers, while during springs, it moves to 120, 140, between 80 and 100 kilometers. And the intensity of the convergence is much higher. So we expect that the spring nip cycle will be playing a major role over sediment accumulation and turbidity formation. Let's see. Other interesting thing is that the turbulent energy associated to the flux also is much more influenced by the spring nip cycle than the high and low discharges of the Amazon. Here we see that despite the salinity structure gets changed by river discharge, the intensity of turbulence is not that different. But when we compare again spring and nip tides, the major differences appear mainly at this region of predominant mud. All right. Well, trying to quantify it a little bit, what we saw of flow convergence between wet and dry periods is about 2 times bigger, while when we compare spring and nip tides, it becomes 4 times stronger. The main reason for that to occur in this graphic, we're seeing the first one is river discharge. We have a whole year in the time axis. This is tidal range. The blue line is the position of the 30 PSU salinity, and the red one is the freshwater limit. So what we see is that during spring tides, the intensity of the cross-shore gradient of salinity gets much stronger. So that makes flow convergence stronger also, and we are expecting to find more sediment deposition and more turbidity. All right. It's just a zoom in. So we suggest this hypothesis. The bottom convergence zone follows the salinity front. So the salinity front displaces seaward during spring tides and shoreward during nip tides, and it's enhanced by tidal range, and we expect higher. So just to conclude this first part, we are seeing now a comparison between these convergence zones and the expected siltation by field data. So it's more or less agreeing in position, but not that much in intensity. As we see in this frontal zone, just in the region of the plume of the Amazon. Acho que dá para desligar isso aqui. The higher sedimentation rates are expected to happen here, and we have higher convergence in the Amazon mouth itself. So what we're trying to do next is to explain why these convergence are not following the deposition rates found by data. You can change the. Go to PowerPoint. Outro. So we start to think about their possible role for internal tides in the context of the Amazon shelf. I'll try to explain you in a. So when we look to the Brazilian equatorial margin, we see huge differences between Rio Grande do Norte and the Amazon. That's basically caused by geological history. But the interesting thing actually is that despite we have this mean slope of 1 to 3,000 in the Amazon, while in the other parts of the coast it's 1 to 200, when we give a closer look to bathymetry, all right. This is a close look to the region of the Amazon mouth. Here we have the North Cape, North and South Channel, and Baía de Marajó. The map is turned about 45 degrees left. What really calls our attention here is this region that's sand dominated. We have stronger slopes, but it doesn't change a lot in space. When we see to the limits of the mud arc of the Amazon, we have really high gradients in this region. And the main feature that calls our attention is that this 70-meter depth contour that in almost all the Brazilian coasts follow the shelf break just in front of the Amazon Canyon. That's this feature. It detaches from the shelf break and goes to the limit of the Subacos Delta of the Amazon. This is another bathymetry I took from an article. We have the same thing, but what calls more attention is those features around here after the 60-meter Elizabeth. And these channels looks very much like ebb channels, ebb dominant channels. But for geologists, they suggest that this is actually a sign of the ancient history of the Amazon. So 20,000 years ago in the glacial age, the coastline was coinciding with the shelf break, and the delta of the Amazon was here. So that's quite conflicting, because I wouldn't expect that in 20,000 years these structures could remain almost untouched. So we're trying to give another possible explanation for that. So we have this sandy dominated region with steeper slopes, but with low variability, where we are expecting that barotropic forcing will be governing the hydrodynamics. And in this region, we have a very sharp shelf break. We have the Subacos Delta of the Amazon with milder slopes inside, but with a very sharp slope at the edge, where we're expecting that baroclinic effects must be the main ones to explain the process. Inside this mud belt, we have high suspended sediment concentrations, and outside of it, the suspended sediment concentrations fall order of magnitude. And in front of this region, right, when the slopes are steeper, we also have a milder shelf break. So we start to think that the internal tides somehow are interacting with the Amazon Canyon and making some influence on the limit of the progression of the Amazon Delta. Another interesting thing is that in this region where we do have the influence of internal tides is also a region where we have carbonatic structures that now are being called the Amazonian coral barrier, Amazonian reefs, and so on. Well, this is a map of the intensity of the slopes in the shelf. As we see, the slopes around here, the sandy region, doesn't change that much. We have almost constant values to the whole platform. But when we look to the limits of the Amazon Delta, we have some regions of very steep slopes of about 1 to 100. That's not pretty. For me, it's quite hard to explain how the limits of the mud could remain the same with a steeper slope like this. And at the region of the shelf break, we see that in this region we have slopes from 1 to 5 and 1 to 10, very, very steep. And in the region of the canyon, these slopes are much milder, about 100 to 300. Going next. Well, what happened with hydrodynamic? When we saw that features, we started to think about, well, we have a numerical model for this, so let's try to figure out if your model is capable to reproduce these kind of structures. So I started to looking at the Ekman numbers to understand if the vertical viscosity suppression is representative, and we find some correlation between the low Ekman numbers and this region where the depths of the platform are greater. So somehow geostrophy could be playing a role on this, and it's quite coherent for the model. It doesn't change much through the whole year from nips, and neither from nips and springs, neither for dry and wet periods. Once again, the convergence of the flow, despite the intensity is not okay, but the position is okay. And also when we look to vertical velocities, we can see this like a convergent cell. So in this region we have the red ones are velocities, are upwelling velocities, and just outside of the mud ridge we have downwelling velocities. So looks coherent, but when we go to morphodynamic modeling, we start to have some problems because the sediment is not getting retained through the whole border of the Subacos Delta. It happens mostly at the mouth of the Amazon, and starting with an initial amount of sediment to the platform, we are losing huge quantities of sediment to the deep ocean basin. That made us think that maybe we're losing some kind of process that acts in controlling the diffusion of the sediment. Other thing that we found is that contradicting field measurements, bottom suspended sediment concentrations are higher always, no matter what we do with the properties of sediment. The concentrations are always higher during the bottom concentrations are always higher during spring tides than nip tides. So we try to explain this by some internal. Lucas, I'll play. This is what happens with sediment concentration. You will see that we start with, and it's only getting concentrated in the frontal zone of the North Channel, but not across the whole delta. And all the sediment that were in this part of the platform were washed to the deep basin. Again, this is about the variability of the concentrations within the nip and spring tidal cycles. So we have a huge reduction of bottom concentration during nips, and we have much higher concentration during springs. This can be explained by many reasons, but we have some hypotheses associated to internal waves also. Let's see. Well, the first hypothesis is that the internal tides that are happening in the thermocline of the Amazon are somehow these internal tides reflecting on the shelf break are somehow acting as a physical barrier to the advance of the fine sediment through turbidity currents to the deep ocean basin. So these steep slopes, we were expecting to have turbidity currents running through the ocean, and actually that's what's happening in the model. So we think that the effect of these internal tides on the permanent thermocline of the oceans is somehow washing the outer shelf and avoiding the sediments from the lutocline to move downwards and go to the deep basin. So these effects maybe we have two possibilities. The residual transport of these internal tides will be shoreward, and this sediment gets accumulated in the shelf, or these currents are capable to resuspend the sediments and offer it to the water column, and the sediments are being transported by the mean flux of the North Brazil current or the plume of the Amazon itself. The second hypothesis we are trying to propose is about the higher concentrations in the bottom during neap tides. What we think is that here we have concentrations during springs and concentration during neap tides, and this is the salinity structure for each moment. So we believe that during neap tides, this pattern of stratification could be generating internal waves, and these waves will be moving to the bottom and intensifying the amount of turbidity during these periods. Because we saw something similar in literature in other places, but the problem is we don't have enough resolution to understand if this process is happening in the Amazon or not. So just to characterize, those are the main. Here we have a cross section. We have three typical pycnoclines in the Amazon. We have a lutocline at the bottom that has his maximum thickness and in this region of about 10 to 20 meters. We have the allocline interacting with this lutocline, and we have the permanent thermocline of the oceans around 100 meters depth. If we look to they change several, about 1/10 to 100 of the real gravity. At the allocline, it goes to 100 times or even 1,000 times smaller, and in the thermocline, it's 10,000 smaller than regular gravity. When I look to when we go to the lutocline, we're expecting waves around 2 seconds of period. In the allocline, we're expecting waves between 3 and 10 seconds, greater than 3 to 10 seconds. And at the thermocline, these waves will be greater than 100 to 300 seconds. So trying to understand in a general view how does these internal waves will behave through the domain, I propose this chart. In the horizontal axis, we have to the right greater Brunt-Väisälä frequencies, greater Brunt-Väisälä periods, smaller Brunt-Väisälä frequencies, and the opposite. And in the vertical axis, we have higher Richardson numbers and lower Richardson numbers. So what we see in the reality is when I have high Brunt-Väisälä periods and high Richardson numbers, I tend to have higher amplitude on internal waves. And in the opposite way, when the periods are small and the Richardson numbers also, we have smaller and more shorter waves, and it tends to turbulent dissipation. So in two opposite, we have those big internal ocean waves with up to 100 meters, and in the opposite position, we have turbulent dissipation by turbulence. And the other diagonal, we have, for instance, in this region, non-stratified fluxes and lentic systems. In the middle of all this, we will find the estuarine processes, and around here, what happens to fluid muds? Well, these are the properties of the Amazon allocline. We are talking about density gradients from zero, almost zero, during spring tides in some places, to almost 10 kilograms per square meter during springs, during neap tides. 3 to 10 seconds of Brunt-Väisälä periods, and Richardson numbers ranging from 0 to 10. And a interesting thing that makes me believe that we can have significant internal waves in the plume is that the the symmetric fluid numbers in the model have reached values of 0.7. So around 0.5, 0.6, we are expecting to start seeing supercritical reduced gravity fluxes that can generate resonances, important resonance effects that can be transported to the alkaline and have some consequence around sediment transport. What else? Well, now looking to the Amazon alkaline, yet we have again, this is a whole year. In the first graphic, we're seeing the intensity of the vertical density gradient, Brunt-Vasala periods, and Richardson numbers. The main thing we see in this picture that the hydrodynamics of the Amazon makes that the Brunt-Vasala periods and the Richardson numbers have some kind of negative correlation. So despite we have through the whole year conditions for internal tide, internal wave formations, we expect that the ideal moment for the formation of these waves will be in the transition between neap tides and spring tides, because in neap tides we have high Richardson numbers, and in spring tides we have high Brunt-Vasala periods. So in the transition between neaps and springs, the conditions will be the most close to the ideal to have the formation of internal waves in the alkaline. Again, what we see in the Amazon is the system is some kind of elliptically traveling from partially stratified to well stratified, and as we know, when we are in the extremes of the main diagonal of this graphic, we don't have good conditions for internal waves. But when we are around here and here, we can have greater waves happening in the alkaline. So now going to internal tides, this is, I think, it's more interesting to understand the big picture of sediment transport in the Amazon. What we see is that the thermocline ranges mainly between 100 and 300 meter depth. It eventually goes up to 60 meters when we have a north current vortices passing through. And the density gradient is about 10 to the minus 2. Brunt-Vasala periods are in the order of 100 seconds, and Richardson numbers are almost always higher than 10. So these properties, this stratification pattern, combined with a extensive shelf and a macrotidal regime, give us ideal conditions for the generation of internal tides. In parallel, this is a picture of the atlas of soliton occurrence in the world, and the Amazon is being pointed out as a place where internal solitons occur with large frequency. So these observations are made by looking the surface roughness and satellite images, and it agrees with the hydrodynamics. So this is a SAR image, and we're looking at internal wave breaking, and this region is right in the place where we think that the sedimentary processes would be being affected by the internal wave breaking. Let's go. Internal waves. Well, once again, as I said, the concentration, the sediment concentration, falls exponentially when we go outside of the mud belt, and this strong reduction in suspended sediment concentration is also associated to the occurrence of carbonate structures to the outer shelf. And recently we got those pretty images from the people of Greenpeace showing that in this region we have about 80 meters depth and waters are crystal clear, and we have this sandy bottom with dune formation. So we expect that these characteristics will be explained by the effects of internal tides. So I started trying to model this internal tide, and that's quite challenging because we need a lot of horizontal and vertical resolution to represent these tides. So I decided to use a 2DV model that's been forced shoreward from the tidal prism of the Amazon and seaward from the tides, the levels itself. But the problem is that we have vertical resolutions up to 1 meter, horizontal resolutions in the order of 100 meters, and time steps about 5 seconds in a domain that is about, I don't know, 500, 600 kilometers. So that computationally, that's quite complicated. And we're working with Z-layer model and non-hydrostatic model also, because we have steep slopes and the vertical momentum starts to be important. Let me see. So here we have a down. This is one of our first models. We're trying to reproduce the formation of the internal tide in the thermocline. And the most interesting thing of this picture is that the internal tide becomes as starts like a sinusoidal wave, and the nonlinearities starts to be more important, and we have this soliton package formation being propagated seaward. So this is agreeing pretty well with the theory and with satellite observations. So it's quite promising, but these models still need to be very developed and calibrated and all the stuff. But for sediment concentration and for sediment transport, the most interesting thing is when we look to the detail of the shelf break itself. These internal tides are reaching exactly the same region where we see those steep gradients in the mud belt. So somehow it makes sense that these internal tides could be acting as a driving processes to this structure of the outer shelf of the Amazon. And when we look to the residual currents caused by these internal tides, only by these internal tides, we don't have the other forcings. It appears that this is mean magnitude and this is cross-shore residual velocity. So red values are positive to the right, and blue values are to the left. So exactly around 70 meters depth, where we have this steep slopes where the sediment of the model was being lost through turbidity currents to the deep basin, we have a convergence zone caused by these internal tides. So we strongly believe that these internal tides are playing a major role in the control of the sediment flux through the outer shelf. And that's it. We'll keep developing this model and trying to formalize this hypothesis, and I hope we can make some contribution to the community. Thank you.
Thank you, Ernesto. We have time for questions. If there is questions in the audience.
So I was a bit confused by the last slide. I thought that the hypothesis was that the internal tide. About the last slide. I thought that the idea was that the internal tides resuspend sediments and then mix them vertically, and therefore prevent the offshore.
We are not sure what's happening, But I think there are both things. We have this part of the residuals suggests that these blue velocities are shoreward, so somehow it's blocking the advance of turbidity currents. But they are also enhancing turbulence at deep waters. I think I've missed some. Where is this slide? We're missing one slide here. Well, we were missing one slide where I show the decay of tidal-driven currents in this region. So we have two things. If you let the model alone with tides and wind and the other forcings, the sediment just flushes through the ocean. So I think this convergence here can explain somehow how this sediment is being kept in the shelf.
And do you have any idea of the bed shear stress exerted by the internal waves hitting the
The
shore?
biggest problem here is that Z model layer, Z layer model, and the shear stresses in this kind of model are not very. The velocities at the very last layer are not very representative. We should try to make some more effort to try to look to these stresses numerically. We are now more like trying to make a conceptual model for the big picture of sediment transport in this region.
No more questions? Yeah.
Ernesto, I think this is very interesting. And to Bob's question about the shear stresses, you generate quite important normal stresses as well. And so my suggestion is to have a look at those as well, because they can really induce a lot of transport.
The normal stresses?
Normal stress gradients. Because you get the stress gradients, so you have quite high waves. And so you get an oscillating normal stress gradient, which can really do a lot on the fine sediments.
It's a good idea. I'm kind of starting this study and moving forward. I'll take a look to them. Thank you.
You put Brunt Vaisala frequency dependent on inverse of Richardson number.
What?
You said 1 over T is proportional to.
No, yeah, that's mathematically wrong. That's not not proportional. It's just that we are observing negative correlation between both. Yeah, no, it's not. That's mathematically wrong. I figured it out after I made the slides. Is that sign is not well represented. But the interesting thing is that when Brunt-Vaisala periods goes up, Richardson numbers goes down in the region of the Amazon we are studying. That's have to do with the dynamics of the region, but it's not mathematically dependent.
Okay, if there is no more questions, I'd like to thank Ernesto for his presentation.